Understanding Physics, and this video is on how to smash the multi-choice paper, because so many students are terrified by the multi-choice paper. Having marked so many, you get very, very bright students do absolutely rubbish on it. So I'm going to give you some tips on how to prepare yourself for this beast, this multi-choice paper. And what we're going to do is we're going to look at some questions and go through these questions. Now, what I suggest you do is have a go at them yourself to start with as a good bit of revision. So pause the video, have a go yourself, and then I'll talk through the answers to each one, and we will see hopefully a pattern emerging. So look at this one, November 2021. These are AQA questions, but OCR, it's the same thing. The battery in the circuit has an EMF of 4.2 volts, negligible internal resistance. What are the readings on the voltmeter when the switch is open and when the switch is closed? Now, basically something you should know about the voltmeter is that it has a very, very high resistance. A perfect voltmeter has infinite resistance. Now, when the switch is open, this resistor here, that has nothing to do with it because it's not connected to anything. So basically you've got this infinite resistance in series with, now the 40 and the 40 together will be 20 ohms. The voltmeter will get all of the voltage. So when the switch is open, it's 4.2 volts. It's either that one or that one. Now, when the switch is closed, what we have is basically, if we could redraw the circuit where you've got 10 ohms there, there's 10, and you've got, and as I said, the 40 and the 40, you should know very, very quickly that's just 20, and then the voltmeter is there. So we're looking at the voltage across the 10 ohm resistor. So that's going to get a third of 4.2. So the answer is D. So hopefully you got that. Tricky little question, that one. Let's have a look at this question. In the circuit below, the voltmeter reading is 0. When the temperature of the thermistor T is increased, the voltmeter reading changes. What will change the circuit to restore the voltmeter to 0? So now, if the voltmeter reading is 0, if I call that point there X and I call that point there Y, then the potential difference between X and Y is 0. In other words, the potential at X is the same as the potential at Y. If we increase the temperature of the thermistor, then you should know that its resistance will get smaller. So if its resistance gets smaller, then the potential at Y will get bigger, because looking at this bottom branch, this potential divider on the bottom branch, which is R and T, R will get a bigger share of the voltage. If the resistance of T gets smaller, then the resistor R will get a bigger share of that voltage, so the potential at Y will get bigger. So how do we get the potential at Y down? Well, one way of doing it is by making the resistance of R smaller. And if we make the resistance of R smaller, then the potential at Y will get smaller because R will get a smaller share of the voltage. And that option is D. So the answer is D. Another way of doing it would have been to make the resistance of P bigger, and then the potential at X will get bigger, and so maybe then the potential at X and the potential at Y would be the same again, and the voltmeter would read 0, but that wasn't one of the options. Okay, so the answer is D. Oh, this is 2019. Does this look familiar? Yes, it does. It's almost exactly the same question. Almost. The temperature of the negative temperature coefficient thermistor is then increased. So again, its resistance goes down. Yes. So how do we get the potential difference? Let's call that X. Let's call that Y. And how do we get the potential at Y down again? Yes, because it'll go up. Decreasing the resistance, it's the same question. Look at that, it's the same question. Gosh. Now, 2018, I've been doing every year. There wasn't a multi-choice question like that, but there was quite a big short answer question. Look it up yourself. 2017, there was this one here. In this network, the EMF of the supply is 12 volts, negligible internal resistance, blah, blah, blah. What is the reading on the voltmeter connected between X and Y? Again, what's the potential at X? Now, looking at this branch here, remember, we can look at the branches separately, can't we? Looking at this branch here, the potential at X will be 1/3 of 12. Yeah, that's 1 ohm, that's 2 ohms. So it'll be 1/3 of 12, so the potential at X will be 4 volts. Looking at this branch here, and again, we can look at it independently, the potential at Y will be 1/4 of 12, because that's 1 and that's 3. So it'll be 1/4 of 12, which is 3 volts. So the potential difference between X and Y is 1 volt. If you connected a voltmeter between X and Y, it would read 1 volt. So the answer is B. The answer is B. Here's one. I did this question here just to make a point. So this is Dave's bonus question. Have a go at it yourself. See if you can do it by yourself. Again, we've got 2 branches. We've got 4 resistors, fixed resistors A, B, C, and an LDR, a light dependent resistor. Again, the voltmeter reading is 0, so the potential at X and the potential at Y is the same. Which of the following statements must be true? The potential difference across all the fixed resistors must be the same. Rubbish. You could have A and C are big and B and the LDR are small, and you could still have the voltmeter reading 0, so that's rubbish. The potential difference across B and the LDR must be the same, and that is actually true. Okay, they're in parallel with each other, yes, but the point is that they are getting equal shares of, see, in this top branch here, in that branch, A is getting some of the 12, B is getting some of the 12, and then in the bottom branch, C is getting some of the 12 and the LDR is getting some of the 12. And if the potential at X and Y is the same, then B and the LDR must be getting the same amount of voltage across them. Yes? I mean, the potential at that point there is 0. So the potential difference from from that point to X is the same as the potential difference from that point to Y. Anyway, I'm waffling now. It's true. The current through the LDR must be 0. No, there's voltages across stuff here, so there's currents flowing. If a bright light is shone on the LDR, then the voltmeter reading will decrease. And that's wrong. If we shine a light on the LDR, then the resistance of the LDR will go down. So the LDR will get a smaller share in that branch. So the potential at Y will go up. Okay. And if the potential at Y goes up, then the voltmeter reading will increase. It won't decrease. And anyway, it was 0, but how on earth is it going to decrease if it was 0 to begin with? So the point I'm making is that very similar questions come up almost every year. Sometimes they just change the numbers or they ask for a different thing, whatever. Very, very similar questions come up every year. And I bet you 20 pence now that on the paper that you do, there will be a very similar question. And the more of these questions that you do, the better you get at doing them, the easier they become. As long as you understand them and you know why the answer is the answer, they will get easier and easier. Therefore, bearing in mind that good revision is either processing information or testing yourself, Do what I did. Find the past papers site, do AQA past papers or OCR past papers. You'll find lots of past papers. Find all the multi-choice questions for a particular topic for at least 5 years, or 5 years is a good amount of time. Copy and paste them into a PowerPoint and then save these PowerPoints in a revision folder. Make sure you can do the questions, in the week before the exam, go through them all, check that you understand the answers to all of these questions. And a very similar question will come up this year. I'm not saying it's the only revision you can do, but this is something else that you can do to revise. This would be good revision. Let's have a look at the photoelectric effect. Let's have a look at the same thing again. So June 2022. Again, have a go yourself, then I'll tell you the answer. In photoelectricity, V is the stopping potential. What quantity is EVS? Now, you should know, because you know all about the photoelectric effect, that these electrons get emitted, yeah? And we can find out how much energy they have by seeing what voltage we need. Like if we make that negative and we make that positive, yes, then what voltage do we need to stop them? Yes, and that's called our stopping potential, Vs. Yes, so what voltage do we need to stop them? And then how much energy do they have? Well, the energy that they have, therefore, is EVS. So EVS is equal to the maximum kinetic energy of the photoelectrons, and so the answer is B. Next, monochromatic light with a photon energy of thingy is incident on a metal surface. The maximum speed of the electrons is doodah. What is the work function of the metal? So we know that the energy of the photon, yes, is equal to the work function plus the kinetic energy of the photoelectron. Okay, and this energy of the photon is HF. Okay, so you've got all the information you need. You're given the energy of the photon. You can work out a half mv squared. Look on your data sheet, mass of an electron, so you can work out the kinetic energy, so you can work out the work function, and the answer is B, that one there, if you work it out. A photon has energy of doodah electron volts. An object of mass 0.03 kilograms has kinetic blah blah blah. What is the speed of the object? There's a very useful equation. I use it a lot. Right, velocity is root 2ke, 2 times kinetic energy over m. And I use that a lot. You use it in SHM, you use it in lots of other things, in momentum questions, sometimes you use it. And basically, change your electron volts to joules, bung it in there, get the velocity, and the velocity works out at about 3 meters per second, ignoring relativistic effects. Moving on. Oh, look at this. We're going year to year to year. Lighter frequency thingy is incident on a metal surface. The work function is thingy. Which statement is correct? So no photoelectrons are released. So basically, do we get electrons being released? Well, what we need to do is do HF, work out the energy of the photons. And if you work out the energy of the photons, you will find that it is bigger than the work function. So we do get electrons released. And then the difference between the two is equal to the energy of the equal to the maximum kinetic energy of the photoelectrons. And if you work it out, I'm sure you're capable. The answer is C. Photons of wavelength doodah are incident on a metal plate. The work function is doodah. What is the maximum kinetic energy of the emitted electrons? It's the same questions again and again. They're just different numbers. They're asking different things. Let's work out the energy of the photon. So E equals HF, or we could say, I generally just basically go straight to E equals hc over lambda. Yeah. And then change that into electron volts. And you get the kinetic energy of the electrons works out to be, and the answer's A. Same questions year after year, yeah? Last one. A little bit trickier, this one. There's a little sneaky bit in here. Maybe you'll spot it. Have a go at yourself. Pause the video. And the answer is, well, now, a beam of light of wavelength lambda, okay, and you're getting electrons being emitted, falling on the metal. Now, the wavelength is halved, but the energy incident per second is kept the same. So the same amount of energy landing on the metal, but the wavelength is halved. Now, if the wavelength is halved, then that means that the frequency is doubled. And so the photons are going to have twice as much energy. Yes, and if the photons have twice as much energy, then the answer is either A or C. So the photoelectrons will have more energy. Now, will we get more photoelectrons emitted? And the answer is no, we'll get less. Now, why? Because if the photons have more energy, then we're told that the energy falling on the metal is the same, therefore there must be less photons. So the number of electrons we get will be less. So the answer is C, is the answer. Sneaky, tricky little one, that one. So, a few other points about the multi-choice. For AQA, and paper 1 is 85 marks, and you've got 2 hours. And so that's like about 1.4 minutes per mark. And that means that you should spend about 35 minutes on the multi-choice. On OCR, there's like 30 multi-choice questions, so you should spend about 40 minutes maximum on the multi-choice. And they have it at the beginning of the paper as well, okay? Don't spend more time than that on the multi-choice. Short answer questions are usually much easier marks to get. On the short answer paper, it usually starts pretty straightforward and easier, and then gets a bit trickier and trickier within the question. And then the next question is the same. It starts easy. I'm not saying the paper gets harder and harder. I'm saying that the question usually gets a little bit more sophisticated as you work your way through. Nevertheless, generally, it's for some of these multi-choice questions, you have to do a lot of work for 1 mark. Okay, so in terms of time well spent, you know, focus on the short answer. The short answers and the long answers tend to be easier marks. Then hopefully you'll have time to spend a decent amount of time on the multi-choice. If you get to a question and you haven't got a clue, and you've spent like a minute on it and you're nowhere near an answer, then just leave it and move on. What you can do is put a little asterisk like that at the top corner of the page. And then if you've got time at the end, come back to it and have another think, and the answer may pop into your brain magically, or at least how to do it. Or in the last 5 minutes, the invigilator should say something like, you have 5 minutes left. Guess. Do not leave it unanswered. You know, I've marked multi-choice, so many multi-choice papers, and it is so frustrating when somebody doesn't put any answer down. Okay, I mean, you've got a 1 in 4 chance of getting it right. Don't leave it blank. So good luck with the multi-choice. Practice makes progress. Practice doesn't make perfect, but it makes progress. Yeah, the time that you put into revision is an investment. And then this big, evil, scary bear won't be as scary, hopefully. And good luck this year. And that's that.